So a quite useful application of limits is trying to observe how functions behave when we go towards infinity. So we can just write x tends towards infinity at our limit. So we could have functions, so we could have a function f of x, and I want to observe how does it behave when I go towards positive infinity. So we read this as x tends to plus infinity. If it was minus infinity, we just put the negative sign. So here, x tends towards or to minus infinity. So x tends to minus infinity. Now, if you observe a function, right? If you compare, if you're growing and growing your number, x will always be larger than 1, right? If you're going forward and forward and forward towards infinity. Also, x will always be less than x squared, right? If this is 2, this will be 4. If this is 4, this will be 16. And obviously less than x to the power 3, less than x to the power 4, and such. Likewise, so if I'm comparing those functions, I could say that this one is approaching infinity faster than this one. It's just for fun. Now, what about 1 over x? What would happen to this if I'm approaching infinity? So if you observe this number, it's 1 over something. So if I do 1 over 1, that would be 1. 1 over 2, we're going towards infinity, right? So we've got our x and y, and we're analyzing how this function behaves. So when x is 1, that's going to be 1. When x is 2, that's going to be a half. When x is 3, it's going to be a third. When x is 4, it's going to be 1/4. When x is 10, this is x, this is y for this particular function. When x is 10, this is going to be 0.1, right? 1/10. When x is 1,000, it's going to be 0.001. When x is, I don't know, 1,000,000, it's going to be 0.000001. So when I get towards, when x tends to infinity, what would happen to y? We can see that y is decreasing. However, it's always positive, and it's becoming a small number, but it doesn't actually get to 0. So we could say that our function is approaching 0, right? So the limit of this function 1 over x, when x tends towards or tends to infinity, that would be 0. Because as we move further and further to infinity, we're getting closer and closer to 0. And you should remember that this function is like that. And if you assume negative values, you would have the same shape but mirrored. So I could also ask you, alright, what about now, what about the limit of the same function 1 over x when x tends towards negative infinity? So if you observe, look, we could do exactly the same thing. We would have negative here, negative here, negative here, negative here. It would be exactly the same table, but with negative values instead. So we would be approaching 0, but we would be approaching 0 from negative values. But it's also 0, so our limit is also 0. So if we go towards negative infinity or towards positive infinity, this is going towards 0, right? And this is also going towards 0. The height of this function is going towards 0. And then, this is actually quite interesting. And it's just a side note, but if you take the limit of this function 1 over x, when x is tends towards 0 from the positive side, so I'm going from here, approaching, you can see that this is going to increase up to infinity. So that's positive infinity. However, if I approach from the left, so same function, but I'm approaching from the left, so I'm going, x is tending to 0, but from the left, from the, here will be the negative values of x. As it's getting closer and closer to 0, our function is going closer and closer to very, very large negative numbers. So the closer we get to 0, the closer we're getting to negative infinity. Now, if you observe those limits, they're different, right? And that's going to be something that we'll discuss in the future, but basically the limits does not exist. When we calculate here, when the limits, they're different, that means there's no limit. Because if you observe from one side, you would get positive infinity. If you observe from the other side, you would get negative infinity. So there's no consistency. And it's like if you go 0.1 to the side, you would get exactly the opposite extreme of values. So there's no limit here. So as you have probably noticed, we can use the concept of limits going to infinity to analyze asymptotes of functions. So let's take a look at a very simple example here. So discuss the behavior of f of x equals 2 minus x and 1 plus x near its asymptotes, and hence deduce their equations. So the asymptotes are going to happen in basically two different cases. The first one is when our denominator goes towards 0. So if this approaches 0, then we will have an asymptote. And also, when we take our limits towards infinity, if there's a limit, so if our function approaches a certain value, then we'll also have asymptotes. So let's take a look at each of those. So what would happen if I'm taking x to be close? Because if you analyze this, for this to approach 0, x would have to be negative 1. Negative 1 is what makes this denominator 0. So I have to observe, what if I approach this negative 1 from the left? What if I approach it from the right? So if we approach it from the left, our function would approach, would it go towards any value? So let's see. I would be making this number very, very small. And this number on top, would it change very much? Well, the part here on top, if I'm going towards 0, I would be, going towards x negative 1, I would have minus minus 1. So this here on top would actually be approaching 3. So it's 3 divided by a very, 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 very small number. This value down here, since our number is more negative than negative 1, the values here, they will be negative. And the values up here, they will always be positive, right? Because this is negative, so it doesn't matter if I'm approaching from the left or right. Minus minus 1, this will always approach 3 in both occasions. But when I approach from the left, the denominator will be negative. So I am approaching infinity, but I'm approaching negative infinity because the denominator will be negative. If, however, I approach this same point from the right, the denominator would be positive. This would be like a very small but positive number, and this would be close to 3 anyway. so a constant divided by a very, very small number that gets each time smaller and smaller, then we would have infinity as well. And in this case, since both of them are positive, then I'm approaching positive infinity. Now, what about the infinities? So when I'm going towards, let's say, positive infinity first. So when I make x's very, very, very large, what happens? So take a look at the function that we have. It's quite an interesting one. Let me use a different color. So we've got 2 minus x over 1 plus x. So I'm going just to change a few things, but I'll still have the same function. Take a look. So let's say that I want to have 1 plus x here on top as well. So couldn't I add and subtract 1? Right? So I've added and I've subtracted 1 on top. And it shouldn't change anything, right? 2 plus 1 minus x is the same thing as 2 minus x. Now, what if I want to split this into two fractions? So I can do 2 plus 1, that's 3. Okay? Minus 1 plus x over 1 plus x. Now, notice that I've taken both negative signs up front and I've written everything as positive. So if you notice, why have I done this? Well, because 1 plus x and 1 plus x, this will be negative 1, right? Negative 1. So our function can also be written as 3 over 1 plus x minus 1. So what would be the limit of this function when we go towards positive infinity? So when we go to positive infinity, what would happen? Well, now, there are two parts of this. This first part, we can split this limit into the limit of each of those pieces. So we can do the limit of the first part plus the limit of the second part. Okay, so we can just add the limits. And now just as I shown you in the previous example, the limit of a constant when you approach anything is the constant itself. So this would be negative 1. Now what about this value? Well, as x increases and increases more and more and more, 3 over something that's increasing, this is a constant. So 3 over anything which is increasing will go towards 0. Right? Because this is going toward infinity, the denominator. So you're dividing by numbers which are larger and larger and larger, so your number will be smaller and smaller and smaller. And you can get as close to infinity as you want to get as close to 0 as you want. So 0 plus 1. 0 plus negative 1. So the limit would be negative 1. So our asymptote is negative 1. And our function would be approaching negative 1. We could even sketch our function in a minute when we're done. X and y. Okay, so if I continue here, x, the next one here would be the other asymptote. What when we go to negative infinity? Well, when we go to negative infinity, this will still go to 0. And down here, it will be a very, very small negative number, right? This will be large, but overall, it will be a very, very small negative number, so negative 0.0000. And you can get this as close to 0 as you want, such that you only have the negative 1 left. So when you approach negative infinity, your asymptote is the same. So now we would be able to plot our graph. So if this is negative 1, this is our asymptote, our horizontal asymptote. And we also have some vertical asymptotes, so negative 1 as well. So our function would look like this. It's just a sketch. This is not up to scale. I'm not really checking here the y-intercepts or anything. But you could just do that, right? If x is 0, then you find 2, so this point here should be much higher, should be 2. But anyway, that's the shape of the function that we're looking at. And this is y equals negative 1, which is our horizontal asymptote, and x equals negative 1, which is our vertical asymptote. Now, that's the last example that we're going to cover today. And so, find, if possible, the limit of 3 minus e to the power of negative x when x goes towards negative infinity, and limit of 3 minus e to the power of negative x when x goes towards positive infinity. Now, in this case, what we have to look for is convergence. Now, the point here is, for example, now that we're talking about coronavirus, and we know that it follows an exponential curve. So what does that mean? Well, it's a function that starts increasing like that, and then the slope gets very steep as you go towards positive values. So for example, if you just observe a function like this one, if you approach positive infinity, will this converge to anything? So will this approach a single value? No. So we would say that this diverges. If this was our f of x, the limit when x approaches infinity would be would not exist. Okay, so it doesn't exist. This limit does not exist. If it approaches a certain value, then it will exist. So given that, now let's observe this question. So we've got limits, two limits of the same function, but approaching different infinities. So let's observe this first one. First, let's take a look at our function. So we have 3 minus e to the power of negative x, right? So if we increase x, if x is going, let's say, towards negative infinity, let's observe what would happen here. So this is constant, so this would just be constant. Now this part, it's minus e to the power of negative infinity. So this is actually e to the power of infinity. Do you agree? So f of x would be approaching 3 minus e to the power of infinity. Now this is not a number. This is diverging. This means that this is not even right, I mean, properly written. This doesn't make sense. But it's just for you guys to understand that this would be a number which is growing each time more, so this diverges. So this limit does not exist. Okay, okay, so this one doesn't. So it's not possible to calculate this first one because it doesn't converge. So it doesn't exist, or it diverges. Another situation where it diverges is when we have those functions just like we saw before. For example, reciprocal functions. It diverges here in the middle because you have one value from the left and one value for the right. So there's no limit here in this point 0 in this example. Now what about the second limit? So if our function is 3 minus e to the power of negative x, however, I'm approaching positive infinity. Now why will this converge? Well, you can rewrite this in a way that perhaps is more meaningful. You could just write this as this, right? And you can easily see that if this number, if this exponent here is positive and increasingly positive, this will approach 0, right? Because you're dividing 1 by something which is larger and larger and larger. In this case, it was the same function, right? It's exactly the same function. However, I was approaching negative infinity, which would flip this up, and I would have e to the power of infinity. And then, well, 3 minus e to the power of infinity, well, it doesn't make sense. And it diverges. But in this case, this will go towards 0. So the limit does exist. So the limit when x goes towards positive infinity of 3 minus e to the power negative x, that's the same thing as 3 minus limit when x goes towards positive infinity of e, well, 1 over e to the power of x. And then since this is a ratio, this is the denominator will always increase and increase and increase. The number will decrease, so all of this will be 0. This goes to 0. So my limit is 3. And that's all for today.